fun stuff too. That's basically it. But there are wonderful processes within those star-forming galaxies, like supernova at the end of stars' lifetimes, that blow stuff out very, very energetically. Sometimes that gas rains back down onto the galaxy's disk, its star-forming stellar disk, to form future generations of stars. So we as astrophysicists need to understand this process if we are to ever have any hope for humanity to understand the ways that galaxies evolve over time. The stuff that forms stars, the stuff that forms planets, the stuff that life comes from. This galactic gas cycling process is extremely important for us to understand that. And we have no idea what it actually looks like.
Oh, sorry, my fault.
Oh.
Okay, try again.
Hey, there we go. All right, scary slide, but bear with me on the graph here. So this is showing us what we as astrophysicists know from simulation. So we have really fancy computers and we can simulate what the gas in a galaxy looks like, that whole circumgalactic medium. So if we were to take just the CGM of a galaxy and look at its temperatures, remember simulated temperatures along the y-axis of this figure, and simulated densities of this gas along the x-axis here, we have what's called a phase diagram. So sometimes astronomers say the CGM or circumgalactic medium is multi-phase, it means all these phases.
Oh
no! Thought I almost had a shot to catch it, but no.
It's not a SpaceDrafts show without some kind of drama. It's every time. Every time.
You're right. I don't think I've seen a cloud for the last 3 weeks and suddenly we have rain. So.
This is what we do. We generate rain for Tucson. Every third Tuesday, rain for Tucson.
This is the rain dance, yeah?
Yeah.
All right, onward. All right, phase diagram. So the grayscale on this is showing the mass of a simulated circumgalactic medium. And if you look on the y-axis here at all of this gray stuff in the background there, all of this gas, or a huge portion of this gas, is at a few times 10 to the 5 Kelvin, so 100,000 degree gas. That's going to be our magic number for this talk here today. So much of the mass in galaxies in the circumgalactic medium is holed up in this a few 100,000 degree phase. We call this phase the warm-hot phase because, remember, astronomers are the least creative people on the planet. It's between the warm phase and the hot phase. Warm phase gas is about a few times 10 to the 4 Kelvin down here. Hot phase gas is 10 to the 6 and up. Okay. Now, if you're looking at these wonderful, confusing, colorful squares here, long story short, these are atomic line transitions that are fingerprints to help us study different regions along this phase diagram. So if we want to study this few times 10 to the 5 Kelvin gas, this warm, hot phase where all of this mass is, we got to look at one of these orange squares. I'm going to give you just the answer here in which one of these we're going to look for. We're looking for this O6 one right there, oxygen 6 from 5 times ionized oxygen. Long story short, it's the easiest one to observe, but it's by no means easy to observe. Okay, so that's from simulations. From theory, we think we know what the CGM should look like and where all this mass should be. Now, what do we actually see when we point our telescopes at stuff? What do we see in observations empirically? So the vast majority, and by vast majority I mean almost all of what we know observationally of the circumgalactic medium has come from what's called quasar absorption lines, or absorption line studies in general. Oh, the sail is coming, I can see it almost tilting again.
We got sandbags now, so.
Yeah. I'll just stand in front of it. So what are these absorption line studies that we know what we know from? So you take your favorite optical telescope. Most of the time, historically, this has been the Hubble Space Telescope for the vast majority of these studies. You point it at your favorite background quasar, which just so happens to be behind the CGM of a foreground galaxy that you're interested in studying. So off the bat, let me explain this a little further. So the light from the quasar, picture a light bulb behind a cloud. The light from that quasar, as it travels from that quasar towards this galaxy, is absorbed by the atoms, is absorbed by the atomic constituents, the structure of this intervening foreground galaxy. So we can use the fingerprints of absorption. Yeah, we can use the fingerprints of absorption. From this gas to study the very faint circumgalactic medium and the atomic transitions that are happening there. Now, so what have we learned from studies like these? So we have learned that the CGMs, particularly this warm-hot phase of CGM gas, contains more mass than every star in the host galaxy. Tons and tons of mass. Extremely dynamically important. Again, this is why when you hear astronomers say stuff like, most of the universe is missing, we don't know where most of the universe is. It's because we have all this mass outside of galaxies, no clue what it looks like, we really don't know empirically what phase it's all in, we have some ideas, but no clue what it actually looks like. So if you're following along from studies like this, one caveat is you have to be lucky enough for there to be a background light source towards the line of sight to this object you're interested in studying. Because remember, we don't care about the quasar, we care about the galaxy in the foreground. But, as you can imagine, we don't get lucky enough very often to have these quasars behind the things we want to study. So, right off the bat, that's a limiting issue. Secondly, you only have information along that one line of sight to that quasar. So if you want to study anything in 2D space, images, morphology, you're SOL. Can't do it. So in essence, we do not have eyes on the dominant matter component of the universe. So I'm not the first person to have come up with this.
Oh my gosh!
We got
Holy
a real monsoon
cow.
here, guys.
This is a real storm.
Anyway, so I'm not the first person to come up with this idea. This has been a well-known issue in astrophysics for a very long time. In fact, all the way back in 1976, Lyman Spitzer said, while the hot gas observed with Copernicus is very similar to the extended corona, suggested nearly 20 years ago, the origin and spatial distribution of the observed coronal gas is not at all certain. So since the 70s, it's been over 50 years we've been thinking about this stuff. So why haven't we been able to solve this problem yet as a field? Well, the answer is likely three things. One, that oxygen 6 transition that I mentioned before, that perfect fingerprint for us to study this stuff, that fingerprint emits light in the far ultraviolet. So remember, light like the stuff you see with your eyes is not the only types of light that's happening all around us. That's being emitted, absorbed, all that fun stuff. There's infrared. If you put infrared goggles, you can see heat. The UV is on the other end of the spectrum, a lot higher energy and a lot bluer than blue, hence ultraviolet. So immediately, shout out to the ozone layer. It's awesome. It keeps us from getting cancer immediately. But it also keeps us from ever seeing these photons from Earth. So, if we ever want to observe this oxygen 6 gas, these photons, the fingerprint of warm hot gas emission, we got to go to space immediately. Got to get above the atmosphere. That light's also hella faint. So, it's extremely difficult to observe as it is. You need hypersensitive optical systems to be able to see this stuff. And you're sitting and staring at single fields for literally weeks at a time to detect just a couple of photons. And this last one is a little bit more subtle. There's an element of luck to this that I believe may have been biasing some of the past results from the absorption line studies like I mentioned before. So on the left-hand side here, this beautiful picture you have been seeing is an actual simulated galaxy just in that warm, hot oxygen 6 component of the CGM. So the stellar disk lies along this horizontal axis there. And these filaments are actually oxygen-6 circumgalactic medium filaments. So if this galaxy is a representation of the real world, what real external galaxies look like, if you were to just point your telescope at a quasar over here, or in region beta, you wouldn't see anything. But if you point your telescope and have a quasar at region alpha, you get lucky and you detect something. So the quasar absorption line results could be biased to making us think this is harder than it is, just to say. Now, adding fuel to the fire here, ultraviolet optics and detectors are historically just terrible in terms of efficiency, and it's really, really hard to get something into space. Until now. So, in the last 10, 15 years or so, there has been an extreme push and a huge revolution in ultraviolet technology and access to space. Just how in the last 10 minutes we've had more rain than the last one. So can you guys hear me in the back okay? Yeah, all right. Screw it, we'll just keep going.
Soldier on.
All right, so what's been going on in the last 15 years in UV astrophysics? So there has been leaps and bounds in detector technology. So on the lower left here, electron multiplying charge coupled devices, EMCCDs, are being developed right now at NASA JPL in LA, in Pasadena, California, by Sholay Nitzat. And Erica Hamden, right here at University of Arizona, develops these EMCCD detectors as well. Manuel Quijada, his group at NASA Goddard Space Flight Center in Maryland. This is Manuel inside of his coating chamber, where he coats ultraviolet optics for high reflectance. So if we want to make a telescope to observe ultraviolet photons that are very, very faint, we need optics that are very good at reflecting those photons. And that's what Manuel does. Microchannel plate detectors have been getting smaller and smaller. MCPs are really, really old, archaic technology in a sense. They've landed on Mars, they're in orbit around Jupiter as we speak. But the key point being, they're getting smaller and smaller for us to put on small spaceflight platforms. And of course, in the news, SpaceX, the Falcon 9, and NASA's partnership with SpaceX in the SmallSat rideshare program has dramatically reduced the cost of sending small payloads into space. And so in this new paradigm that we're currently living through, that I've been calling the Wild West of space astrophysics, Aspera was born. So Aspera, my wonderful little mini fridge in the sky that will float and tell us all of the wonderful secrets of the CGM. So here's a quick view of the Aspera team. I'm not going to read all the names, but I'll just say I'm Carlos Vargas, I'm the PI. Erica Hamden is the deputy PI, another faculty member. She's sort of second in command. Han Chung is the project scientist. And Tom McMahon is the project manager. And as you can see, the team is solidly centered, managed at the University of Arizona, just right down the street. And I'll also point out the coloring scheme. You might see some names are hard to read. The color coding here is blue for early career faculty and postdocs, orange for graduate students, yellow for undergraduates, purple for early career technical staff and engineers. And you'll be very happy to see as well, we are over 50% early career. We're one of the very few NASA projects that are actually mostly early career. This is something I'm very proud of. I also...
This is wild.
I also got to shout out ANT, Ascending Node Technologies, is one of our partners. This is another local Tucson company that is helping us with flight software, concept of operations, orbit selection, all of that fun stuff. So shout out to ANT. So hot off the press, you guys are among the first people on the planet who aren't on the team to see our final CAD design for our SpaceDrafts, the payload the instrument that will take these measurements for the very first time.
Holy shit.
And here's what it looks like. Now, it's going to be challenging to see where everything is, but... Oh, we've got a roof leak.
Oh no!
We'll survive, y'all. All right. Main components of the SpaceDrafts. So we have, if you follow the path of light here... Hold on, I'll give everyone a second to relink it.
My computer! Go ahead and finish.
All right, onward. Let's go. So main components of the SpaceDraft. If you follow the path of light through the two identical entrance apertures, you'll eventually hit an OAP, off-axis parabolic mirror that is coated with enhanced lithium fluoride. Remember that higher reflectance UV coatings? Bounces light to our gratings, which act sort of like a prism to separate the light into its colors. And then those colors
Here's power? How? Nothing else lost power. I don't know. Nothing else lost power. Is it because the plug is down there?
I bet you our entire electricity just got shorted.
Huh?
I think the greatest sun's one.
Yeah, I think it's because our plug is down there.
Welcome back!
Hold my beer.
Doutor, e que maldição tu traíste pra cá que tu está parceiro? Você não estava allá porque me dijiste, I got really late, I'm trying all the undergrads. No, just I've been up in the last 20 minutes. Yeah. Oye, ¿y dónde traiste el huracán contigo? No, dale.
Do we know where this is going? Do we know where this is going? Okay. Do they have another cord?
Show does 3 speakers and astronomy in the news every month, or they used to. I'm gonna stop the live stream.
Try out and try it again, or
Alright, maybe we'll still be in business. Okay, good. Woo! No, yeah, Susie trying to jury rig something. I know. She's badass. I've been live tweeting her drama. Carlos talking, and then there's like sail. Yeah, just like lightning.
Like, I for sure thought when it stopped before. I surprised we got our like.
That's what my weather app said. My weather app said peak rain chance 7 p.m. Goes down to 0 after that.
Well.
There was a cluster of people just standing there with you to talk.
Yeah.
That is interesting.
At the end, they were very
That is interesting to see here. Let me tell you.
Yeah, it's interesting.
We love those from CGM.
I do not
I am so nervous for Susie. She's a badass, but like, I'm still nervous for her. Is that Trent? you. Is it?
I connected with the cam link. It should be working.
It is not.
Cam link is.
I'm just turning it off and on again. Cool. Nope, that's the. How did we solve this before?
It was info. Hang on. Tell me when it's on the menu.
Okay.
Is it on the menu?
Hold on. Now. There you go. Do it again. Again. Again.
Oh, good.
I love that we're just live streaming all this. I never stopped live streaming, so just live streaming it. I've been live tweeting all of this, by the way. I tweeted some good videos of Carlos talking while I pan over to the downpour.
Thank you so much for rolling with the punches.
Yep.
We should take you.
At least it's quieter now. What's up with the projector?
It's warming back up. It wasn't turning on, Matthew. I just switched the plug.
Uh-oh.
We got the power come back up.
Yeah, I can see it's on. I just thought it would have shown something by now.
Yeah, how long does it take?
There it goes. There you go. You had to push that button. Huh? There it goes. Back in business.
What? So just this?
This whole thing. Just all of this. My goodness. This is the wackiest SpaceDrafts
This
ever.
is
Wackiest SpaceDrafts
something.
ever.
See if I can get away with not moving the screen.
The sandbags are gonna. Oh, one of them dumped everywhere.
Toss it over and
Yeah.
we're gonna this and I'm gonna get a room and
Okay, are we ready?
I think so.
Yeah. Can we do the? Can you do some audio test? Oh, it got turned down. Okay, can you talk?
Test, 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 test. Can you guys hear me in the back? Way back? Oh, I see some thumbs.
Yeah, I see thumbs. I think we're good to go.
All right, hey everybody, we're back. So Mother Nature didn't cooperate for the first half, but looks a little bit better now. But maybe I should knock on wood or something. Anyway, let's pick up right where we left off, y'all. So as I was saying, you guys are among the first people who aren't on the team who are able to see this wonderful hot off the press CAD model of what Aspera actually will look like, since we're beginning the build of this instrument as we speak. So, following the path of light, because remember this is a telescope, following the path of light through these two identical entrance apertures. So light will come in from space through this way, come down these rectangular baffle regions. Inside of these rectangular boxes are specially engineered vanes that keep scattered light from bouncing around to get through the entire system of our telescope, because remember we're looking at extremely faint light, so any extra light that we don't want really screws things up for us. So as that light goes down right through the barrel, it'll hit our OAP, or off-axis parabolic mirrors, which are coated with those wonderful high-tech UV high reflectance coatings. They bounce to our gratings. These gratings sort of act like prisms. Prisms, that separate light into their colors. But these gratings do that way more efficiently in a smaller package. And that separated spectrum of light, the colors of light, then gets sent down to our detector, our microchannel plate detector, which is at the heart of the instrument here. The detector is shared by both of these identical apertures. So what you see on this side is the same as on that side, except on this side we're showing like a cutoff where on the left-hand side, where that teal area would represent a shroud that covers the whole thing. So this is just so you can see the innards, basically.
Oh, sorry. My mistake. Okay. There you go.
Awesome. So we're not reinventing the wheel here. This is a design inspired by the FUSE telescope, the Far UV Spectroscopic Explorer, launched way back in the 90s when I was a baby. It's, again, 2x long slit spectrographs. This instrument, Aspera, even though one of these mirrors is only about 5 centimeters across, will be 2,000 times more sensitive than the Hubble Space Telescope's Cosmic Origin Spectrograph instrument for the purposes that we're using it. So that isn't to say we're way better than Hubble. Heck no, we're not. We're a lemon zester. Hubble is a whole kitchen full of tools. We do a lot more than we can do, but we're really damn good at zesting lemons. So this instrument is comprised completely of proven technologies. We're not testing new tech at all. We're using regular old optics for the most part, regular old detectors that have been flown a million times before, coatings that are pretty close to state of the art. And here, of course, banana for scale, so you can see roughly how big this is. This is a full 1-to-1 3D printed model of the instrument. And here's Afaq Khan, one of our wonderful graduate students, stealing the payload 3D model at one of our reviews. Okay, so what are we going to use this wonderful telescope to do? We're going to look at these galaxies to observe that oxygen-6 warm hot gas emission in the circumgalactic medium of the galaxies. These are 6 of our 21 total targets that we have on our target list, of which our mission is to observe a subset of 10 and map 3. And remember, 3 would still be 3 more than anyone's ever done, so this is a pretty big deal. You might notice a similarity between all of these. Anyone have any ideas on one similarity between all these? I see a hand in the back. What are you seeing?
Well, yeah, I was going to ask if they're all edge-on for any reason.
100% correct, yeah. So these are all edge-on galaxies,
Nice.
meaning we're seeing disk galaxies with their plane oriented, so we're seeing it from the edge on, sort of seeing the crust of the pizza, if you want to think of it that way. Now, why might we be looking at edge-on galaxies, which is your question? This is so that in projection, we can immediately distinguish what's in the star-forming disks of those galaxies, which you can see in these images, and what's in the circumgalactic medium, which would be above, below, outside of it. Because again, what we're interested in is seeing that CGM that no one's ever seen before. So who knows what lies in the dark regions of this image that we're yet to find? Okay, so what will Aspera be capable of doing? So here are some mock observations. So you can see our instrument's response, our system response. This includes things like spacecraft jitter, our resolution, that kind of fun stuff. So if we were to take this simulated galaxy that I showed way back before the Poseidon came from the sky or whatever, you could see these wonderful features in that simulated galaxy very clearly in our mock observations. Oops, sorry, I went too far. And the way that we build images like this since we are what's called a slit spectrograph. So our field of view is only one of these rows in this sort of diagrammatic showing you how this works. We build the image by going row by row for a super long time per row, and then building an image together like I just showed it stitched together there. So with Aspera, we should easily be able to distinguish these wonderful filaments that we don't even know if they exist or not yet. So what are some major technical challenges that we are running into right now as we build Aspera? So the biggest issue to keep our detectors alive, again, contamination is a killer for us. We have to pump the interior of this detector down in high vacuum all the time, 24/7. On the right-hand side here is a payload mass model. So here's a model of what the payload would look like, but it's made to be robust in mass, so it's made to be an accurate representation of the mass of our payload so that we can shake it up in the spacecraft model and make sure it doesn't break or cause any modes for when we launch that will destroy things. Speaking of the spacecraft, so that company that we go to buy a spacecraft off the shelf, so to speak, is the University of Toronto Institute for Aerospace Studies Spaceflight Labs, or SFL. And here's the spacecraft qualification unit. This is very, very close to what our actual spacecraft will look like. And here's us in Toronto visiting SFL during some of their testing work. We are here at the Rogers Center in Toronto watching a Blue Jays game. As you can see, we are a very low-budget NASA project. We're sitting all the way up in the nosebleeds. Oh, can I get the clicker back?
Oh, sorry. I'm trying to troubleshoot some stuff over here.
So on the right-hand side here, here's a CAD image of what the spacecraft will look like, more or less, once the solar panels are deployed. They're right now stowed on the qualification unit at its side. They would open upwards in this image. Oh yeah, my little mini fridge. Roughly the size of a mini fridge. So it could fit on a desk. Not a big problem. Not a very big satellite at all. Whoa. Oh, sorry, I thought I went too far. All right, so I have a wonderful multiple choice question, and I've heard that we're giving out a prize to whoever answers this question right. So I ask of you, wonderful audience, in general, roughly how much does it cost to launch an Aspera-sized spacecraft, we're about 60 kilograms, you know how big we are, into low Earth orbit? Is it $10 million, $1 million, $100,000, or $10,000 as of today? I saw your hand go up first. So you say A, $10 million? Very good guess, incorrect. I'm going to someone else. Oh. $100,000, correct. You won a prize. So just about 10 years ago, this would be about over $1 million to send a 60-kilogram payload into space. But thanks to those recent improvements with the small-sat rideshare program, literally, we can hitch a ride on a SpaceX rocket for just about 100K, maybe 200 or 300K, but orders of magnitude, we're astronomers, that's close enough. So what does that rideshare actually look like with NASA? So this is an actual picture. It looks cooler than it does on the projector on my screen, but whatever. This is an actual picture of a SpaceX rocket with its fairing opened up, and you can see the wonderful Esper rings where each of these small little payloads attaches onto the fairing. And then all these Starlink satellites that are destroying our night sky, that brings us internet. So then that fairing gets closed up. You can see the outer portion of the fairing in the back portion of this picture here on the left. But the fairing gets closed up, slapped onto the top of a rocket here in this portion, shot up into space. Eventually that fairing opens up, and then each of these little payloads, when it gets to low Earth orbit, gets popped out one by one. They're spring-loaded, and they're off on their merry way. So that's what the future of Aspera will look like. So a little bit about the program. So Aspera is a funded program in the NASA Astrophysics Pioneers program. That means we have a budget of $20 million to make this happen. So the emphasis here, this is not your father's NASA spaceflight program. Emphasis is on training the next generation. It's meant to be high risk, high reward missions. This is very atypical of NASA. NASA is one of the most risk-averse agencies on the planet. The schedule is intensely aggressive. This is a crazy understatement. So from beginning to end, 5 years. So that means we design the entire thing, build the entire thing, test the entire thing, launch it, do all the observations, publish the papers on the observations within 5 years. It is a crazy breakneck speed for a schedule. And I'll show you where we are on the schedule in a slide, so you'll see that. We don't know when we're actually going to launch yet. So this is a perfectly great question to be asking. So the rideshare details. It's up to NASA to pay that couple $100,000 for the rideshare. Thankfully, it's not in our project budget. However, we won't know the details of the rideshare, what orbit we're even in, until about a year out from launch. And we're not quite there yet. Yeah, we'll know a year out from launch. So here's the schedule. We are here in roughly October of 2023. So we began in April of 2021. We just had a series of NASA reviews, PDR, CDR, preliminary design review, and critical design review. The critical design review marks when we have completed our design. There's some hanging chads here and there, so to speak, to finish up, but we have now entered the payload assembly and testing phase, which will run all the way up till end of 2024 or so, when we then are enter the spacecraft INT phase, when we put the telescope into that off-the-shelf spacecraft. And then at the end of 2025, roughly October-ish of 2025, we will be launch ready. So depending on when NASA can get us one of those ride shares, looks like we'll be launching at the end of 2025. Great, so takeaway message here, wrapping things up. Again, the CGM is a wonderfully important thing to study if we ever want to know how galaxies evolve, how planets form, how stars form, that sort of thing. We must understand the complexities of the circumgalactic gas cycling mechanism. ASPER is an astrophysics pioneers far ultraviolet smallsat mission. We are aiming to be the first to map the warm, hot circumgalactic medium. We're building it right down the street at U of A. And the build's happening right now, and we're planning to launch at the end of 2025. Thanks very much for listening. So I think we have time for 1 or 2 questions. Anybody?
Way in the back.
You mentioned earlier that you needed to pump
Can you louder?
So you mentioned earlier that you needed to pump the satellite back. There are few reasons you need to do that in
So I think what you might be referring to is we needed to pump down the NCP detectors. Yeah. Okay. So why do we need to do that, and why can't we just use an inert gas or something? It'll take forever to get the gas out of the infinitely long microchannel plates and the sort of maze that in which they would fill up with gas. So if we wanted to pump them down to use them again, it would just take a long time to pump them down. Nicole might have a better answer for that, because Nicole's also, in addition to being our contamination control lead, she's blushing. She's also our microchannel plate detector lead, so Nicole can answer all your detailed questions about that too. Any more questions? All right, thanks again, guys.
Thank you so much. And thank you for valiantly pushing through the chaos of the brain.
My gosh.
So because of all of the excitement, we are running a bit late, so we are going to have only a 10-minute intermission. So please rejoin us at 8:40. Please make sure to thank and tip your bartenders. They were very kind to us, accommodating all the rain. Also feel free to come and chat with us, buy our merch, give us donations, get the pair of Eclipse classes for next April. Also, whoever won the trivia question, please come talk to us. You will get a sticker or something. And then we will be back at 8:40 for Astronomy in the News.
So I ruined the live stream apparently. I don't know. It quit, and once it quits, you can't reconnect. Can you record the rest? So I'm streaming through the default one, which I assume is going to pop up on our channel when it's done. Okay. So I can use for us. stitch it together.
Under all of the circumstances, I'd say,
Yeah.
geez, I'm just psyched we're doing it at all again. So
I know. We lost a good fraction of the audience, but did you see that chunk of people standing out there in the pouring rain listening? That's some dedication, man. I don't know how they could do that.
yeah. All right, we go sell
Huh?
that stuff.
Are we muted?
Yes, we're muted. Well, of course we are. Jackie and Danny are only doing 2 stalls. Yeah, it was a guy in a black shirt. I think it was Carlos' friend. Yeah, it's the guy Carlos is talking to.
I think I told you.
They can self-identify. He doesn't want his prize, he doesn't get his prize.
Yeah, in the excitement, we were holding these when we went to a stage.
Oh no! I haven't actually seen them. Yeah, they're cool. Nice. I actually don't Wackiest SpaceDrafts ever.
Probably the worst problem we've ever had.
Go see the folks in the back.
Alright, cool.
We got a prize for you. Yeah, I was in California for 6 months. I had an internship. It was good, yeah. I had some medical issues, but otherwise.
Yeah, because the monsoon we got happened. I was making fun of Dr. Bugger because, he's Puerto Rican, I'm Dominican. I'm like, why'd you bring the fucking hurricane here? Like, because I come here all the time. I never bring this kind of rain.
Oh, well then you haven't been coming to the right SpaceDrafts, I guess, because we always seem to trigger the rain whenever we want to have a show.
So that's the funny thing. Since the one in October, that was the last time it happened, it's been pretty consistent without the rain.
There was one in the summer, July or something.
August might have been the one I missed, because I was here for July. July was like pristine.
Yeah.
August might have been the
Because
one
I was watching them from California when they were here, and there was one that was in there.
I imagine it was the one in August.
I don't remember. Yeah, maybe.
Because I was here for the one in June and July. It went up cut out a hitch. But yeah, so I've been dragging the undergrads here to be like, yo, like this is some cool shit. Like bring ass out. What the fuck?
That's awesome. Glad you did that.
I wish I could. Like I believe how much this shit is worth. So
Yeah.
about helping out. Because like to me, it's a minimum. Like the undergrads should be wanting to see what the grads are doing and working together. Like it's the bare minimum, at least in my opinion.
Yeah. Well, we would love to get undergrads involved in this part of the show. We'd be happy to have volunteers help us. Yeah. You want to join our team? Happy.
Because I know, at least for myself, I was doing some research on what am I talking about. So I was working with Dr. Nathan Smith and was doing work on type 2 and supernovas.
Well, we always need more bodies to help, like, put the show on, set up, tear down, all this stuff that we did today. We can always use more help, and we would love to get undergrads involved.
Oh, no. I'll talk to everybody, but I know for myself, definitely will help.
Can you email our email, SpaceDrafts?
Will do. Because I know
No, it's not that. There's a business card.
Because I've been talking to Lily as well about wanting to do like a SpaceDrafts night in Spanish as well.
That would be awesome. Have you heard of Astro Charles? You're the guy?
I'm one of their main guys.
Okay, great. I think that would be. I would love that. I would love that. Let's do that.
Would you, I know you're super busy, but at some point, would you send them maybe like a flyer or something that we can put in our
We don't have
Nurse
any.
would love this.
We don't have any flyers. We do have business cards.
Okay. We can scan and I can put everything and make it pretty and buy your
Yeah, there's business cards back there. If you ask the person at the they're in the money box. Ugh. Can I ask you a favor? Yeah, can you give me a glass of water?
You're bandaged all the way up there.
It's a
We'll be
compression.
back in 5 minutes.
It's a
Just a
compression
5-minute
dressing.
warning.
It's a compression dressing for swelling.
Yeah.
But get this, I started taking antibiotics where I can't. Oh, I told you this on Monday, so you know about that one. Today I got this paste put on that causes headaches and body aches and dizziness. I'm having a great time. I'm having just the best time. Thank you so much. Of course,
You ever just put puberty paste on your feet?
Oh yeah. And so today I got this paste put on.
Oh, the nitro paste?
Yeah.
What's it called? Did you call it nitro
Yeah,
paste?
that's what it's called. I'm surprised you remembered it.
Well, because it sounds so ridiculous.
It does.
Well,
But get this, it causes-
is nitro short for something, or is it like branded like nitro paste?
I think it's
like
nitroglycerin. No, that's not right. That's an explosive. Nitro something.
I mean, some you do take.
Maybe it is.
I mean, if they light your foot on fire, that might be a improvement.
I mean, well, you could like take nitroglycerin for like heart shit, right?
That's true. Maybe it is
But
nitroglycerin.
like for your, I don't know.
Yeah, actually, because it's a vasodilator, so that must be.
Oh, yeah. Okay.
It must be it.
It's
So it causes.
rubbing nitroglycerin on your.
So it causes headaches
Oh, no.
and body aches and dizziness. I currently do have a pretty good body ache, pretty good headache and body ache. Yeah, I'm having because it's like a really severe vasodilator.
It
Because of blood
affects
flow.
it does.
It affects everything. But it's because they're worried about blood flow, so this is to increase blood
I
flow.
just would have guessed that the cream would at least try to like localize it, but I guess that's
no,
hard
it's
to
everywhere.
localize.
Yeah, I have a headache right now.
Oh, jeez, I'm
I'm having
sorry.
just the best time.
One day.
And today I had a psychiatry appointment, and then Friday I have an oncology appointment.
The universe is just like.
Yeah, sounds good.
Would you like another doctor appointment?
My gosh, I was just now. I was like, I don't have anything tomorrow morning, right? I was just like looking at my calendar.
Can you turn that down?
Yes.
Sorry. In case the feedback didn't tell you, we are back with astronomy in the news. Please take your seats so we can get started again. Okay, we're just going. So we are. Yes, I'll leave this up to Jackie and Danny to get your attention again. So without further ado, take it away.
Do you have the clicker? What? Do you have the clicker?
No.
Here's the clicker.
All right, what's up, nerds? It's time for Astronomy in the News, also known as the Astronomy Comedy Hour, with me and Danny. I'm Jackie. I'm a postdoc at Stewart. That's Danny. He's a postdoc at Stewart, too. And here we have come here to tell you about what's going on in the sky and in the news. Usually we do like 2 or 3 news stories. We have like a grand old time. We take up the entire segment. I can't do that today. I have to apologize in advance for that. I can only bring you 1 news story tonight. My fellow space cadet Danny has also joined me in solidarity with 1 news story. Partially, not much is going on right now. Like, not really like in the world, but in the sky.
Something's happening in the world.
So things can fall apart anywhere in the world, but the universe just keeps turning on, and that's great. It just keeps going. Well, I don't know if it's rotating. That's not my problem. Here in my universe, though, I am begging the James Webb Space Telescope to give me money and time. In fact, I'm begging them to let me point the telescope at some very special black holes, which are special because I said so. And it is my job to convince the Space Telescope Science Institute, which is a real place, to let me have money to point the James Webb Space Telescope by October 25th, so I cannot talk anymore. Okay, so this weekend, you might have noticed that your shadow looked weird. I really hope that you did not actually look at the sun to notice that something was weird. But if you're at SpaceDrafts, I bet my bottom dollar that you were out looking at the eclipse. So around 9:30 a.m. this past Saturday, the moon passed between the sun and the earth, casting a shadow on the earth. If you were lucky enough to leave Tucson, where we had about 80% coverage, the path of the total annular eclipse got to see a perfect ring of fire, which occurs because the moon is at the furthest point of Earth in its elliptical orbit. So it's not big enough to cover the entire sun. But there isn't a song about a total annular eclipse of the heart, so really, why do we care? And that's why we're pairing with BetterHelp. For 3 months of post-eclipse therapy for when you blinded yourself. What I really mean is that we have eclipse glasses, as Lily mentioned before, for a low donation of whatever the hell you want. So if you like SpaceDrafts, you want to tip us and whatever, you can get your eclipse glasses here. And also not 3 free months of BetterHelp. Okay, well, to be honest, partial eclipses are pretty run-of-the-mill occurrences. It happens once or twice a year, so really, who cares? An annular eclipse, though, happens every 1 to 2 years. And of course, the real spectacle is the full eclipse, the next one of which will be this coming April. Some quick facts about annular eclipses that I Googled today. The path of annularity, which is the real word for it, is about 100 miles wide on Earth, and depending on the orientation, it can last anywhere from a few seconds to 12 minutes is the record. But unlike the total eclipse, you don't get an easy view of the sun's corona, and very unfortunately for Tucson, it does not noticeably cool off. But some other cool things do happen. So you might have noticed the pinhole effect, which you can see in this lovely picture behind Logan. So when light from the eclipsed sun travels through a small aperture or a pinhole, you can see the shadow of the eclipse. We'll find out in a moment where you can see that shadow of the eclipse. Projected behind it, great. Okay, and you can do this by poking holes in paper, using a pasta colander. My fellow Jerseyan before was talking about how galaxies are pizzas. I'm talking about pasta colanders. We've just brought the whole East Coast to you. Or you can simply look through the leaves of a tree, as you are seeing here. So the real story here, of course, is the friends we made along the way. So here's a fun collection of some of us SpaceDrafts and Stewart Observatory members of the places we went. Oh, the places we went. I didn't get to go, but at the end of the day, we are dorky sky nerds just like you. Not me, but you. Some of us went to Monument Valley, some went to White Sands National Park, others went to Albuquerque, and those of us who are but tiny simpletons who want to look back to the very beginning of the universe with the James Webb Space Telescope went down to campus at 9:30 in the morning to see the 80% eclipse. all of us at SpaceDrafts hope that you went somewhere cool too, and that you have big plans for the total eclipse in April. I'm sure there will be a long waiting list to camp at any of the national parks, but if you can't get in, you can rest easy knowing that there will be 75% covered in Tucson. So hopefully there are no more telescope deadlines in April, and I will get to actually go be a dorky sky nerd with you. I must bid you adieu now. Goodbye.
Yeah, speaking of BetterHelp and all that James Webb ranting, I think you might want to, call him up and, have someone to talk to for all that. Okay, so I guess staying in the solar system, but actually also on here. I would say normally if you're walking around like the Utah desert and there's you stumble upon a half pound of rocks, you'd normally be like, who cares, right? It's rocks. But what if those rocks were from outer space, which is what actually happened almost a month ago, although you didn't just happen upon them, they were placed there purposefully when the return capsule of asteroid material from the OSIRIS-REx mission successfully touched down in the Utah desert on September 24th. And it became only the third ever successful asteroid return sample mission. The first one done by NASA after the two Hayabusa missions from Japan. And this is the one with by far the most material. And not only did this news happen in Utah, but it's actually very important for here in Tucson as well, because this mission is being led out of the Lunar and Planetary Laboratory here at the U of A, including the PI, Professor Dante Loretta. So that's very exciting. Go LPL, yay. Okay, so what is OSIRIS-REx? What did this mission do? What was it for? So the satellite launched in 2016, and then it kind of, ambled to an asteroid named Bennu and reached there in late 2018, where it entered orbit, took a whole bunch of pictures, figured out what was going on the surface, and then 2 years later, in October of 2020, it kind of just, boop. Yeah, it just kind of pogo sticked its arm into the asteroid and picked up some material. The surface wasn't quite what they were expecting. It was a little, spongier, I think, so they were kind of, what's going on here? No, not slurp, please, not slurp. That would be a very nasty, like a chunky smoothie. Oh, ew.
Like cement.
Yeah, like cement. What you love to drink in the morning. So it picked up a bunch of this material, and then it turned around and scooted back to the Earth, where when it got close, it yeeted this return capsule towards the Earth, and then that's when it touched down in Utah just about a month ago. So why is this interesting? I don't want to knock asteroids, but it's a rock, come on. But it's a cool rock. It's a very cool rock. And this is because this asteroid is, I've offended someone. No, it's a cool rock. Yes, because this asteroid is about 4.5 billion years old, kind of a fossil record of the early solar system. I mean, right, there are pieces of asteroids and whatnot that hit the Earth, meteorites and whatnot, but you can look at them to learn about the composition of the rock, but for example, if you're looking for organics, it would be contaminated pretty quickly by biologics here on Earth, but this material is pristine. It is just from the asteroid itself, and so you can look at it to, is it gonna get louder? Choo-choo?
Yes, it is.
Yes, it is gonna get louder.
Yes, it is.
Okay, I'm gonna go for it. And so you can look at this material and learn something about what these asteroids were like at the beginning of our solar system that helped form the Earth. So, just last week, they kind of unveiled the initial studies of what was in this capsule. And so the first thing was that there was a lot more material than the mission originally required. So they had about 250 grams, although they don't have an exact number yet for how much is there. And the mission requirement was only 60 grams. So I think this is probably the one time a 300% error is like a cause for celebration. Not error, but you know, a 300% difference in number is normally a bit of a concern. But here, that's great. A lot more material to take a look at. And so they unveiled kind of the initial studies of the composition of this material and found that it is very carbon rich, as well as containing sulfur and water-bearing clay minerals, which, again, I feel like this is my lot in life to talk to you at Astronomy in the News about why water is important and why we look for it, because it's important for life. And so this is telling us that asteroids like this may have helped to contribute to the early Earth's water and carbon budget, which of course was necessary for creating life and for being here to experience that wonderful rainstorm earlier. So what's next? So they'll keep studying this wonderful pile of dirt. It'll be shipped across the world to a bunch of different collaborators. They'll look for more complex organics. And so we'll learn more about what was going on in the early solar system when the planets were forming. And the satellite is also not retiring yet. So after it yeeted off the return capsule to come back to Earth, it has moved off now to rendezvous with another asteroid called Apophis, which you may have heard of because this is one of those asteroids that, you know, every like 3 months there's a headline that's like, oh, X asteroid's gonna hit us in X year. That was one of those asteroids, although I don't think it's going to. So it's gonna head off there, where in the late 2020s it will enter orbit to study another asteroid to learn about what rocks were like when the Earth was forming and how we got the materials that we needed to be alive today. Thank you.
Thank you very much. I could not see any of those slides, but I'm sure they were wonderful.
You didn't have to stand back there.
I got stuck there. Our second and final speaker of the night is Dean Denton from the Lunar Planetary Laboratory, who will be talking to us about hunting for sneaky ocean worlds.
Hello, everyone. Thank you for staying. I'm Dean Denton, and I'm a postdoc at the Lunar and Planetary Lab. I really like frozen margaritas and having a stable job, and right now I don't have either. But you can fix that. So today I'm here to talk to you about, I made my slides and forgot them, so we're gonna find out together what I'm here to talk to you about. The search for stealth ocean worlds. Now you may ask yourself, what is a stealth ocean world? It's an ocean world where we didn't think it was an ocean world, but it is an ocean world. Now, you may ask yourself, what is an ocean world at all? That's okay, that's okay. Two of the most famous ones that you may be familiar with are Europa, that's on the left, it's a moon of Jupiter, and Enceladus, which is on the right, it's a moon of Saturn. We know these are ocean worlds because we're pretty sure that the ocean is there today and it's affecting what we can see on the surface. And in the case of Enceladus, there are literally geysers coming out the bottom, so it's like, wow, the ocean is literally coming out, it must have one. Very easy. But it is not so easy everywhere. This is a schematic diagram, so when I say ocean world, the Earth is an ocean world because it has oceans, but we're not going to talk about that today. Today we're going to talk about worlds that have this kind of structure, meaning they're cold, they've got ice on the top, but they're not that cold because they have a liquid water ocean beneath. Why do we care about these? Well, the astrobiologists think there's life there. I just think they're really neat. Now you may ask yourself, how do we find ocean worlds? That's also such a good question. I'm going to break that up into kind of two categories. The first is orbital evidence, and the second is geologic evidence. Orbital evidence is basically if we look at the orbit of these moons around their host planet, sometimes we can tell that moons that are on semi-elongated orbits that are close to their host planet should generate extra heat in their interiors because of that orbit. But the second thing is geologic evidence. If we look at the surface of these moons, get a load of that. You know, they're heavily fractured. There's usually not a whole lot of craters because the surface is getting resurfaced all the time. And that's because the ocean beneath the surface is interacting with the overlying ice shell to generate geologic activity. So If we see stuff going on the surface and it looks recent, that's probably an ocean world. This is the trivia question, folks. Which of these lesser known moons, so not Europa or Enceladus, which of these is also thought to be an ocean world, meaning that we currently agree? Your options are Io, Ganymede, Rhea, and Iapetus. Yes? Ganymede, you're so right. You're so right. It's okay. It's good to be right. It's good to be right. There actually have been arguments made for all of these, but come ask me later if you want to know what those are. Some of them are really funny. How is Io an ocean world? Well, what if it had ice? And then it lost it. Don't worry about it. Magma ocean, so true. Ocean world, got him. Yes. Okay, but I don't want to talk about any of those. Those are all so good, but we don't want to talk about that. So this is the Saturn system. I want to talk about the Saturn system tonight. And specifically, I want to go here. Where is here, you might ask? Well, it's Mimas. You guys heard of Mimas?
Yeah.
Yeah. I love Mimas. It's so good. Most people, if they've heard of Mimas, have heard of Mimas because it looks like this. And yeah, let's just get out of the way. You're right. It does, in fact, look like the Death Star, and that is so cool. But it is actually even cooler than that because it's what we think might be a stealth ocean world. And I'm going to explain to you why that is. This isn't a trivia question because, I mean, it's kind of a weird one to ask you guys, but so do you think that Mimas is bigger, smaller, or the same size as the Death Star? Yes.
It's bigger.
It is bigger. Shout out to the front row for knowing their stuff. You're doing great. Yeah, Mimas is about 2 times larger than the Death Star, and that's the Death Star 1. I couldn't find good estimates for the second Death Star, but if you use the most recent estimates, the second Death Star is only 200 kilometers in diameter, so it's still smaller than Mimas, so don't try to get me on that. Okay, skipping that, I don't care about that. Okay, so, is this an ocean world or not? Well, it's a little weird because the orbital characteristics of Mimas are a little funky. Earlier I said that we can kind of tell based on orbital characteristics whether a moon should be an ocean world. Well, Mimas is a little guy. It's very small. It's only a 200 kilometer radius, which for a moon is very small indeed. But it has a relatively high eccentricity, and it's relatively close to Saturn. It's less than 3 Saturn radii away from Saturn, which is really cool because if you look up at pictures of Mimas, you get really great ones like this, where you're like, are you kidding me? Where is Mimas? Well, it's right there. It's right there, obviously. Go on NASA Photojournal and you'll get this and you'll be like, awesome. I'm getting so much geology from that. Anyway, because Mimas is really close to Saturn and slightly eccentric, Saturn should be doing something to Mimas. But that doesn't seem to be the case, which has led us to think that either what Mimas is currently doing is recent, or maybe Mimas has actually been frozen the whole time. But that's not the whole story. Here's the thing. I showed you those pictures of Europa and Enceladus, and they looked really cool. The surfaces were really smooth. That's because they've been resurfaced, because there's an ocean present that's doing stuff. If you look at Mimas, am I allowed to use profanity? It looks like shit. Look at it! It doesn't... It's just covered in craters. Is this a joke? Okay, yeah, it's heavily cratered. And there's not a lot of other stuff going on. It's mostly just craters. There's no cryovolcanism. Everybody always wants there to be cryovolcanism, which is when it's volcanism, but it's water. And those craters appear unmodified, so if you go in, do your geologic mapping, well, they just kind of look like they formed and then nothing happened. So, the geology that we're seeing is not consistent with an ocean world. But, the thing is, this thing is closer to Saturn than Enceladus, the one that actually has cryovolcanism. It has a higher eccentricity, which means it basically has 40 times more potential for stuff to happen. So, Despite that, there's literally nothing going on. What does that mean? Well, originally we thought this meant there was no ocean, but we may actually have been wrong about that, which is so fun. But we're still trying to figure out why. Basically, when Cassini went to the Saturn system, and Cassini is the spacecraft that went to the Saturn system in the 2000s through, I'm bad with numbers, but don't, if you're gonna hire me, forget I said that. Okay, it doesn't matter when it was there, you can Google it. It measured Mimas's libration, which is basically its wobble as it orbits Saturn, and found that it was wobbling a little too much, and they were like, that's so crazy, what's that about? And the thing is, if you do the math, that means that there has to be something weird about the interior of Mimas to make it do that. And there's two options, and they're both really fun, but one of them is definitely more fun. So one is that you have an ocean. So this would be the structure. You have a rocky core, a liquid water ocean, and then an ice shell. And then because of the ocean, it wobbles more. But the other option is that what if Mimas's core is just really weird, right? Like what if it was elliptical for some reason? Don't worry about how that could happen. That's also a possibility, but if you run the numbers, the ocean is more likely. So after they got these measurements, they were like, well, I don't know, like maybe it is an ocean world after all. I have no idea what that's about. So how can it be an ocean world? You might be asking yourself. Maybe it's just me, that's okay. So all of these things have to be true. You have to form an ocean at some point somehow, but then you simultaneously have to build up this largely unmodified surface. You can't make any other geologic features, which you should get if there's an ocean. So you somehow have to keep the ice shell thick enough that there's an ocean there. Yeah, it's just that easy, you know? There's one way to test this, and I'm going to tell you about it real fast because I did it, and if you want to know more, you can talk to me afterwards. One way to test this is, can we make the craters on Mimas if there's an ocean? Because the thing is, if you make a crater big enough and there's an ocean there, you should punch through the ice shell and reach the ocean, right? That's something that we think has happened on Europa, for example. But the thing is, oh, is that happening on Mimas? We don't know. So the Death Star crater, the one that makes it look like the Death Star, I've circled it in red, that's called Herschel. It's the biggest crater on Mimas by a mile. It's almost as big as, it's bigger than the radius of Mimas, I think. Math is hard. It's very big. And it's so deep, it's 10 kilometers deep. That's so deep, you guys. So there's no evidence that it punched through the ice shell because ones that punch through the ice shell do not look like that. And we have no idea how old it is either. But I've run some models with impact simulations to try to make that crater, and they kind of look like this. Ignore, that's Pluto. I didn't have time to make a new video, but this is what they look like when I do the models. Yeah. So true, that's not what they look like. They actually look like the upper right. I have to do it in 2D because computers suck, man. So what I tried to do is see, okay, how do we make that crater? Because we know it's there. We're pretty sure an ocean has to be there. How do we reconcile those two things? Well, I used the present day estimates of how thick the ice shell should be if there's an ocean there, and I punched right through. That's the ice, that's the ocean. That didn't work at all, so I had to make the ice shell thicker. Oh, it works now if I thicken the ice shell over time. So then yeah, that doesn't really matter. What I found is that the ocean needs to be thicker than it is today, but it has to be there, which is really interesting. And I can't remember what the next slide is. Awesome. Okay, so the takeaway from that is, and again, if you're actually interested in my science, I'll talk to you about it whenever you want. The data suggests that Mimas has a pretty thick ocean today, and by thick I mean like 30 kilometer plus thick ocean, which for a body that is that size, quite large. But if we simulate the cratering on its surface, Mimas has to have had a thinner ocean and a thicker ice shell at some other point. If you put those two things together, guess what? Mimas's ice shell has been thinning over time and its ocean has been thickening over time. The ocean is growing. Awesome. So that's why we think that Mimas might be an ocean world that doesn't look like one. It's different because it's young. All of these other oceans on these other moons have been there a while, but not Mimas. This ocean is geologically recent and it's growing right now. So if all of you stick around for like 10 million years, we're gonna see it. We're gonna see evidence of it. Yes. So if Mimas has an ocean today, that suggests kind of a different pathway for how we get ocean worlds in our solar system, meaning maybe you don't form a moon as an ocean world at the start. You don't just get an ocean, you can force an ocean down the line, turn a body into an ocean world that wasn't an ocean world before. And that's why Mimas is called a stealth ocean world. Yep. Thank you. Okay, I can take questions. Do you have questions about Mimas, other moons? Yes.
Yeah, so the idea that the Herschel crater is older than the ocean, is there a possibility that the large impact that created that crater led to the process that made the ocean?
Oh my gosh, I ask myself that question all the time.
Can you repeat the question?
Yes. I'm so sorry. Yeah, so the question was, we think that Herschel formed when the ocean was thinner than it currently is. So the question was, could the formation of Herschel itself actually contribute to that process? Because impacts do deposit heat into the bodies in which they form. So the answer to that question is, unfortunately, Herschel's actually too small to do that. It does deposit heat, so it does make the area around it a lot hotter, but it doesn't change things on a planetary scale. If you were instead to think about the formation of the Pluto-Charon system, and if you assume that that was formed by one body hitting another body, which many of us do, an impact of that scale could basically flash form an ocean. This impact was big, but it just wasn't big enough. Yeah. Yes. The question is Mimas' orbit getting closer to Saturn, and could that be doing it? We don't fully understand how old Mimas the moon is. If you look up age of Saturn moons, you'll find a bunch of people arguing with each other. And so the answer is maybe. The problem is the Jupiter system is so convenient. There's 4 moons, and 3 out of 4 are in these like really nice resonant orbits. In the Saturn system, there's a bunch of moons, and anything could happen. So yeah. One possibility is that the eccentricity of Mimas got pumped up relatively recently, and I think that's something that people have been converging onto, is that Mimas was in a more stable orbit in the past, and then if you pump up the eccentricity and start adding tidal forcing to Mimas, then you start forming the ocean relatively late. But the other option is that you just form Mimas relatively late in general. It's very difficult to tell the difference. Any other questions? I hope Mimas is your favorite moon. Maybe top 3? Okay.
Thank you so much. Also, I'm sorry, I think I have to count our own moon as my favorite moon.
I do like our own moon.
I mean, like, would we be alive without it?
Right.
So thank you all so much for your patience with the rain. Thank you for sticking it out with us. We hope you enjoyed it and that it was worth all the excitement. Our next show will be November 21st, so the 3rd Tuesday of November, again at 7:30 p.m. Hopefully we will be back. Hopefully we will be back out there and not stuck under here. Also, don't forget that there is Nerd Night next Tuesday, October 24th. Right?
Yes.
And I think we still have a bunch of the. So yeah, come talk to us. We will, and you have some if you're interested. Other than that, thank you again all for coming. If you go back in there, make sure to thank and tip your bartender. Feel free to come chat with us. We'll be sticking around for a bit after the show. And otherwise, we hope to see you next month.